Our speaker this evening comes with an esteemed background as CEO of Fivetran. Please welcome George Fraser.
Thank you. So, I'm here to talk tonight about a benchmark that we did at Fivetran last summer, comparing the three major data warehouses that we support. I'm the CEO of Fivetran. I was the technical co-founder of Fivetran, so I will be able to answer your questions, maybe. Fivetran is a fully managed, fully automated data pipeline. Fivetran syncs your company's data from all of these places into your data warehouse continuously and automatically. It's the easiest company ever to explain. I'm going to talk about a benchmark comparing performance. But first, I want to give you a little bit of context about some things. First of all, this is the most important bit of context, the difference between OLTP and OLAP databases. This is a database beat-up. Maybe some of you really know and love databases like MySQL and Postgres. I'm sorry if this is stuff you already know, and this is very obvious to you, but it's amazing how many people who are experts in databases aren't aware of the difference between OLTP and OLAP databases, and that's really important. So OLTP databases are most databases that you're familiar with. Databases like Postgres, MySQL, Oracle, Microsoft SQL Server, and they're designed to run queries like that. Queries that get one row, that update one row, that delete one row, maybe a few rows. They're optimized for that use case. And these databases are used everywhere. On every website, there's no OLTP databases. The other kind of databases is OLAP databases, which are often called data warehouses. And they are optimized to run queries like this, where you aren't working with one row, you're summarizing across all of the rows. So this would be a very simple example of an analytical query. Tell me, for all of my GitHub commits, how many commits are there per author? Because I think that's a good metric of developer productivity because I'm an idiot. That would be an analytical query. Maybe not a very good one, but it would be one. These are typically run by analysts or by BI tools when you're running reports. And there are two completely different kinds of databases that do this. There is no database that is good at both of these things. Do not believe SAP. It is not possible. The design choices that make you good at OLTP will make you bad at OLAP, and vice versa. And this talk is about OLAP. That is the kind of use case that Fivetran supports. That's the kind of use case that we benchmarked. So, just a very brief history of SQL databases, specifically around OLAP, not OLTP. So SQL was created in the 1970s. It was not made by Larry Ellison, although Oracle was very important in popularizing the use of SQL in their database. It was created by two scientists at IBM, Don Chamberlain and Raymond Boyce. It was based on academic work by a man named E.F. Koch. SQL is really old. It's kind of astonishing how old SQL is and how popular it is. SQL is so old that it is case insensitive. Just, like other popular programming languages, like COBOL, for example, another case-insensitive programming language. This isn't really a thing people do anymore, but it was a thing in the 1970s, and SQL is like the last man standing from that era. But don't let that fool you. SQL is not dying. SQL is growing. SQL is undergoing this kind of renaissance in the analytics and reporting world. More and more people are learning it. More and more tools are being developed specifically around SQL. Other methods of doing reporting are falling away. SQL is kind of becoming the new Excel. Even though it's 50 years in, it's having this second wind where it's becoming even more popular. And again, I'm talking about an OLAP use case. It's not in databases. We all know that it's used in databases, but it's undergoing this renaissance in data warehouses over the last 5 years, and it's not going to stop. So SQL started in the 70s. The first data warehouses were basically just databases that were being used for OLAP purposes. They were not fast. The first databases were quite slow, and in order to work around the slowness of the data warehouses that existed at that time, people invented this thing called an OLAP cube. Now, an OLAP cube is a special data structure that allows you to run specific kinds of queries really fast. So the way an OLAP cube works is that if you have an underlying data set, let's say you have a bunch of sales that have occurred over time, what we're going to do is we're not actually going to store all the individual sales. Instead, we're just going to keep track of specific combinations of attributes, like count how many black bikes were sold, 425. Count how many blue bikes were sold, 534. We're going to discard all the row-level data, and we're just going to remember these aggregations. And what that allows us to do is to run queries like this. These very simple OLAP queries will work on a data structure like that. If you think about it, you can figure it out. Like you can actually sort of special case these kinds of queries and run them against this aggregate data structure. And this aggregate data structure is really small, so it's really fast. So you can run queries fast like that on a computer from 1990 if you use an OLAP cube. However, it's very limiting. So you can only do these very specific combinations of dimensions and measures, that's what they call them, that you planned ahead. If you Google OLAP cube, you'll just see endless stuff about how people hate OLAP cubes because of this. But they were a necessary workaround of the slowness of data warehouses at that time. However, now they're going to go extinct. I think you would be hard-pressed to find anyone who disagrees with that. They're still around, just for legacy reasons, but they're no longer necessary because data warehouses have gotten so much faster. And the real inflection point in that was C-Store. C-Store was the data warehouse that changed everything. It was created by a group of scientists at MIT. It is a column-oriented database. And that is a really important distinction to understand. Forgive me if you already know this, but this is really worth knowing if you don't know about it. The difference between a row store and a column store. Most databases are row stores. What that means is that if we have a table, let's say going back to GitHub again, we have a row here for every commit, for every file, how many lines did we add, remove, or change. This would be like something you would get out of Fivetran GitHub integration. If you store this in a row store, the way the database actually stores it on your disk drive is it goes back and forth like a typewriter. So it writes it out kind of like that blue box right there. It writes the job, the first commit, and then the file name, and then the number of rows added, and then the number of rows removed, and then it goes to the second row, etc. So the data on disk more or less ends up like this in that order. The column store does the transpose. So the column store stores all the values from the first column. So we write down all the commit shots, and then we write down all the file names, and then we write down all the number of lines added, etc. And that is way, way faster for OLAP queries. And if you run a query like this example, for many reasons, it will be much faster. The simplest reason is that you actually scan less data. So if we want to run that query, if we're using a column store, we can actually skip reading the job, and read the file, and then we can skip added and skip removed, and you can just read the columns that we're actually referencing in that query. Whereas in a row store, you have to run over all the intermediate values. That's one reason why column stores are faster. It's the reason everyone understands. In reality, column stores are faster for like 20 reasons. Once you make this choice to represent the data differently, you have to rewrite the entire database. You need a different query planner, a different execution engine, you have a different in-memory representation. You use different join algorithms and different aggregation algorithms, and you use different compressions. Everything is different once you go down the column store route. And it makes the database way, way, way faster for OLAP queries. It makes it way slower for OLTP queries. So this is not a better way to make a database. This is a better way to make an OLAP database. In our very abbreviated history, the next event, the first version of BigQuery comes out. I feel like some people are going to be mad at me from the t-shirt raffle because there was kind of a mix of dates. There's sort of two dates for all of these. One is when became available in beta, and one is when it became available in general availability. So 2011 is when BigQuery became available general availability. It was in beta in 2010. Each one of these actually is 1 year before was in beta. So BigQuery was an internal tool at Google called Dremel for several years before this. In 2011, they made it available to the public. The problem was the version of BigQuery that launched at that time was not very user-friendly. It couldn't really do large joins. If you wanted to join a big table to a little table, it could do that. But if you wanted to join a big table to another big table, it wouldn't work or it would be extremely slow. And for whatever reason, Google invented their own non-standard SQL-like language. It was close to SQL, but not quite the same, just different enough to be annoying and kind of prevent other people from adopting it. For whatever reason, they did this, and that dissuaded a lot of people from adopting BigQuery. So even though BigQuery came out in 2011, not a lot of people were using it at that time. And the other big problem with BigQuery is that there was no delete or update. You could only append data, or you could drop the whole table. Those were the only options. It was kind of a classic Google thing. It was like, well, as long as everything about the rest of your system is perfectly hygienic and under your control, then this works fine for you. Works at Google, doesn't really work for anybody else. Redshift came out in 2013. Redshift had a huge impact on the data warehousing and data analysis world. Redshift was the first data warehouse that was good, that was cheap. Redshift was comparable to other enterprise data warehouses like Vertica, which is what CStore became. CStore was commercialized as Vertica. It had comparable performance to those enterprise data warehouses, but it was a tenth of the cost, and it was right there in the AWS console. It has an interesting provenance. Amazon did not actually write Redshift. Amazon bought the source code from ParExcel. So ParExcel was sort of they had a good data warehouse. They had only sort of an okay business, and they sold the source code of their database to Amazon. Amazon integrated it with S3 and some other things, and then rebranded it as Redshift and launched it as their own data warehouse. ParExcel actually didn't sell to Amazon; it sold to EMC, I think. So it was funny. They sold the source to Amazon, and then later they sold the company to a different company. But that's where Redshift came from. It made a huge impact. It was like Redshift was the only data warehouse in existence once it started to take off. A ton of tools, including startups, including my startup, really came into existence because of this phenomenon, all of these people switching to Redshift. In 2015, Snowflake became general available. Snowflake was in stealth mode in 2013 when Redshift came out. Snowflake was a from-scratch data warehouse designed to run on the cloud, in this case on Amazon. Snowflake had a fantastic implementation. Arguably, it was the best data warehouse released to date at the point that it was announced. The thing they did that was really different than Redshift is that they stored the data in S3. They were not actually the only ones to ever do this. BigQuery fundamentally works the same way. Because it's not S3, it's Colossus, which is the system underneath Google Cloud Storage. But it's basically the same principle. It sounds kind of crazy when you first hear it. Like, I'm going to have a data warehouse. I'm going to have all this data, but I'm not going to have data in the actual computers that are the data warehouse. I'm going to have it over here in different computers that are S3. Why would I do that? It sounds like a terrible idea. Like, isn't that going to be really slow to transfer the data back and forth? Counterintuitively, if you sit down and you do the math on how long realistic, complicated queries take, and how long it takes to transfer, those columns of data from S3, it doesn't actually take that long. It turns out that it's workable to have your data sitting in a different set of computers than the computers that are processing it. Because most of the time you spend is going to be doing joins and shuffles and things. No matter what your implementation, that's going to end up sucking out a lot of your time. Or compute bound is the term that people use, not IO bound anymore. And there are some huge advantages doing it this way. When you set up your system like this, you can turn on a new virtual warehouse in 1 second. You can just say, I would like a new warehouse with this many nodes. And all you have to do is just assign a bunch of computers to that group. You don't have to move any data into them. All the metadata about what the definitions of the tables are and things is stored in a high-performance distributed database. So you can scale up and down on demand. And the other really big advantage of Snowflake, from my perspective, is that it just works. Snowflake, being a pure cloud service, is when things go wrong, they have more of an ability to find out what happened than say somebody who's operating a data warehouse that's installed on your own nodes. I mean, I'm just sort of speculating, but from my perspective, we've observed over many customers that it is more of a turnkey system, and I think that's really the fundamental reason for why. If you build a cloud service right, it's easier to get to that really, really high user friendliness. Harder to get to that when your software is being installed on other people's instances. So even though they were a little late to the game, Snowflake became general availability in 2015, and they started to really take off in 2016. Google, however, was not to be counted out. So they don't actually call it BigQuery V2. There was just a series of changes to BigQuery. However, in 2016, BigQuery started to get a lot better. They fixed all of the things that were really annoying about BigQuery. They implemented a new join algorithm so that you could do large fact-to-fact joins, so that even if your schema was a little crazy, it would still work. They dropped their homegrown custom SQL dialect and implemented a standard SQL dialect based on ANSI SQL. And they implemented delete and update so that you can actually change data after you put it into BigQuery. And this combination of three things made the difference. It made BigQuery usable to people outside of Google. And once you got rid of those annoying things, it has some really compelling features. BigQuery charges you, it's a pure shared service. You only pay when you run the query. And when you run the query, they'll allocate as many nodes as that query needs. So all queries basically take about the same amount of time. It's like opening a Gmail account, and yet if you give it a really big query that sucks in a lot of data, it can allocate hundreds of nodes to run that. So there's some really cool things about BigQuery. And so as a result, where Redshift was really looked like it was going to run away with the whole market in 2013, brings us to today, there's really a horse race between the three of them. And that's what we've seen at Fivetran. Whereas the majority of our customers coming in 2014, 2015 were Redshift customers, now we really do see about an even three-way split between Redshift, Snowflake, and BigQuery. Naturally, people ask us, which one is the best? Which one should I use? Some people, they come to us and they already have a data warehouse. But some people come to us and they're trying multiple and they're not sure. And we got this question more and more, and we really didn't know the answer. And I went around looking for benchmarks, and I didn't really like any of them. For reasons I'll describe later, when I compare it to the existing benchmarks, I did not think any of them were very meaningful. They were done correctly, but I just didn't think they were representative of what real users were going to do. I had heard lots of things about them. I heard people say that, that Snowflake was, had these cool features, but that Redshift was still actually a lot faster. I heard people say that BigQuery was really expensive in practice. It has a completely different pricing model, so it's hard to compare, but I heard that claim. But I also heard the opposite claim, that BigQuery was ridiculously cheap and people couldn't believe it. So I heard all kinds of things I didn't know what to believe. And I couldn't find any benchmarks that really compared them in a way that I thought was right. And so I decided we should do our own benchmark, try to do it really fairly. We're a neutral vendor. We don't have a dog in this fight. So we started working on that late last spring. And when you do a benchmark, you have to make about 1 million decisions. So the first decision you have to make is what data are we going to query? So we queried the TPCDS data set. This data set is a bunch of tables that represent the historical sales activity of an imaginary retailer. So it's a Snowflake schema, but it has multiple fact tables. This is actually just one part of the schema. So there's the source sales fact table, which I think has about 200 million rows in the example we did, which is small, and I'll explain why. It's small compared to what a lot of people do benchmarks on. There's also a web sales fact table, and there's a catalog sales fact table. And they all have in the hundreds of millions of rows. And then these other tables have much less rows. So that's the classic Snowflake schema. So we have a big table in the center, and then you have smaller ones as you go out. The queries we ran are the TPCDS queries. So they are generally pretty complicated queries. They all have joins. Some of them have a few joins, and then they kind of aggregate. Some of them are really complicated. That's not even the whole query there on the right. So this one has multiple subqueries of large tables, which are then joined back onto other large tables, so they really hammer the data warehouse. These are complicated queries. These are the kind of queries real people actually make. Real people don't have perfect schemas. They don't have the perfect data pipeline that denormalizes everything into one giant table. They have some things that are a little bit messy, and they work that out by running complicated SQL queries. So that's what we wanted to test. So these are good queries from our perspective. And you might be asking, what is TPCDS? So TPCDS stands for Transaction Processing Council. They are basically a bunch of database vendors. What happened was that, as you know, vendors like to publish benchmarks showing that their database is the best and everyone else is terrible. And a bunch of vendors decided to get together and form this nonprofit called the Transaction Processing Council. And they said, we're going to make the ultimate benchmark. We're going to make this benchmark that no one can cheat. It's going to exercise every feature of the database. There's going to be all these strict rules about how you run it. And then we'll all agree on it, and we'll publish it. And then everyone can run their benchmark and submit them to be audited. And then the world will know whose database is really best. It was a very noble idea. They made this great data set and all these great queries. People still cheated. They figured out how to cheat it. So it didn't really work out. The idea of all the vendors doing the benchmark independently did not really work out the way they hoped. However, it's still a really useful benchmark. And for us, we don't want to cheat. We're going to try to make these choices in a way that's reasonable, that really gives you a realistic comparison. So it was a really good foundation for us to do our benchmark. What do I mean by not cheating? If you want to run TPCDS without cheating, this is what you need to do. First of all, do not run the same query twice. That is too cache friendly. You're just asking the data warehouse to just remember the answer from the previous time and give it back to you again. Lots of people do this. You should not do that. Even if you change the query slightly, you're still asking for an unrealistic answer. Even if you change the where clause a little bit, the data warehouse might cache one of the intermediate results from the previous query plan. That doesn't mean you don't want to allow any caching. Caching is a feature of data warehouses that you should try to trigger. You just shouldn't make it too easy. So you should only run each query one time. And another thing we did is before we ran all 99 queries, we just did a select star order by primary key, limit 100 on every table, just to load every table. So we're basically telling the data warehouse, I'm going to query these tables. If you want to cache, I'm not going to tell you exactly how I'm going to query them, but if you want to cache them, you should do that now. And that, we think, is a fair, reasonable approach to give the cache a chance while not being too helpful. The other thing, this is a little bit more controversial, is I think you should not use partition keys. So partition keys are this feature of data warehouses. They're sort of like indices in databases. You can designate one column, and what you're basically saying is, I want you to take this table, and I want you to split it up into lots of little tables based on the value of this column. And this works incredibly well if you have a where clause that refers to that column. If you have a where clause that refers to that column, the query planner will just figure that out and it'll just skip all of the partitions that are not relevant. It works too well. It's a little bit of a gimmick. It does happen in real queries. So it's a valuable feature to have in a data warehouse. The problem is it works so well that if you use it fully in your benchmark, you're just going to get way lower queries than users are actually going to get. And in my mind, it's the queries where the tricks like that don't work that are the ones that really matter. That's the performance that you really care about. What is the performance when the easy tricks don't work? So to me, the right way to do a benchmark in a data warehouse is to not use partition keys. You still want to know if the data warehouse supports partition keys, but it's more like a checkbox. It's like a feature. You don't need to really benchmark it because it's pretty straightforward how it works. In your general purpose benchmark, you should not have partition keys. You should apply compression encoding. People do have compression encoding in real data warehouses. That's one of the benefits of the columnar format is it compresses better, so you should definitely do that. You should use a realistic scale. A lot of benchmarks use really large data sets with really large warehouses with lots of nodes. The thing is that in our experience, most customers are dealing with data sets on the hundreds of millions of row scale for most queries. And what they're looking at, they don't want to pay the biggest price for the biggest warehouse that's available and then run it against a petabyte data set. They're trying to run against a couple hundred gigabyte data set without spending a ton of money. So you should use a scale that is relevant to whatever user group you actually have in mind. There are users who have petabytes of data, and for them, you want to do benchmarks like that. The users we have in mind generally have data sets that are not that big. And lastly, you should compare costs. This seems sort of obvious, but a lot of benchmarks actually don't do this. My favorite are the ones where they compare themselves to competitors, and they have a really big warehouse for themselves and a really tiny one for the competitors. Sort of obviously unfair, but that does happen. None of the ones that I've mentioned here have been guilty of that, but that is the thing that's happened. So you should compare not just the speed, but the cost of getting that speed. So, what did we find? First question was, which data warehouse is the fastest? So we ran both Snowflake and Redshift in the $2 an hour configuration. And BigQuery, it doesn't have a price per hour, they just charge you per query. So there's just the BigQuery, there is no node size. And we found that we're not that far apart. Note that it is a log scale. Snowflake, so BigQuery was the fastest in draw time. Remember that BigQuery, because there is no warehouse size, it does have the opportunity to allocate more nodes. It's a little bit funny to think about. BigQuery had the fastest median time. There are some outliers. You look at these guys, queries that are really far to the right, and this one here with Snowflake. These queries are cross joins. I've done a list of them. They're like the kind of queries you write by mistake. They don't even make sense when you think about them. I think what TPC was trying to do was actually simulate an analyst making a mistake. I don't think it's terribly important that you run these kinds of queries quickly. That's why I use the median. I think it's important that you don't crash, but I don't think it really matters if you do a cross join really quickly. It just needs to run for like a minute, and then the person who wrote it realizes I must make a mistake, it's taking too long, and it needs to query. So that's why it's the median, not the mean. And the other interesting thing to notice about BigQuery is there's kind of a minimum time. You can never get under a second with BigQuery. That's because it is a shared service, right? You're just going to this big pool of instances. So there are higher fixed time costs with BigQuery. But in general, for reporting, that's not a big problem if things always take over a second. This isn't like a website where you're trying to load really fast. It's okay if it's 2 seconds of BigQuery to run. Snowflake was just a tiny bit slower by this metric. There's a little more spread. And Redshift was a little bit slower than Snowflake. These are all good times. You should not buy a data warehouse on the basis of these differences. Remember, this is one particular benchmark. You change some things around, things can move around by 1 second in either direction. This is not a huge differentiator. And really, we shouldn't be surprised by that. Any benchmark that tells you that a good commercial data warehouse is way slower or way faster than the others is a little bit implausible. Most of the really important techniques for building a column store data warehouse were outlined in C-Store, about which many papers were published. It would be really weird if one of these was way slower than the others, because they kind of all know the same things to do. So this should give us confidence that they're not that far apart, that we basically did this right. Not huge differences between them. They're all fast. This is good performance. You're querying tables with hundreds of millions of rows, and you have a pretty small warehouse here. $2 an hour is a really small data warehouse. So they're doing really well. The other question we asked is cost. Which warehouse is the cheapest to run? Comparing Snowflake and Redshift is really easy because they're both configured in a $2 an hour configuration, right? The problem is, how do you compare BigQuery? BigQuery charges you per query. So what does that mean? You could take your Redshift queries and say, well, how long did all the queries take together? And how long did the cluster then have to run to do all that? How much did it cost? $2 an hour. But that would be a very unrealistic comparison. That would be way too favorable to Redshift, because the implicit assumption you're making there is that you're running Redshift at perfect utilization 100% of the time, and real customers are not like that. You do not get 100% utilization out of your data warehouse. In fact, you get much less than you would think. So we did a study with a bunch of our existing users where we looked at the historical usage from their system tables and found that the median Fivetran user has a Redshift cluster of Redshift users that is only active about 20% of the time, which may seem really low. Like that seems like a big waste. But if you think about it, this actually makes sense. If your queries are finishing, most of them, in less than 10 seconds, which they need to be because there's a human waiting for them on the other end, they better finish in less than 10 seconds. I mean, how many analysts and people refreshing Tableau dashboards and Looker dashboards do you really have? It turns out you need a lot of people at your company to actually fully occupy a data warehouse that returns each query in less than 10 seconds. So typically, you should expect that most data warehouses will be have pretty low utilization. There are exceptions. There are companies whose data warehouses have a queue all day. And for them, the price trade-off is severely in favor of systems like Snowflake and Redshift that have the per hour pricing model. So with this assumption, 20% utilization, we can make a meaningful comparison of cost. We can say, for BigQuery, we just know the price for each query. And then for these other warehouses, we can say, okay, assuming an imaginary user who's just sort of sitting there running TPCBS all day at 20% utilization, how much does it actually cost them to run each of these queries? It all turns into just a number that you multiply the time by to get dollars. And what we found is that BigQuery is about twice as expensive as Snowflake and Redshift under these assumptions, which surprised me a lot. I kind of figured it would be like the previous one where you do all the tricky math and you find out they've priced themselves just to be competitive. There's a pretty big caveat here, which is that it all depends on that assumption of your utilization. And it also depends on if you have a very spiky workload. So if you are a company that runs queries very infrequently, or that runs queries frequently, but they're mostly small, and then occasionally you have a really big one that you still need to return really fast, BigQuery is going to be a way better deal because of the pay per query model. If you are a company that has thousands of people hitting these dashboards every day, and you are running a data warehouse at full utilization, then BigQuery is going to be a bad deal. That pricing model is going to be a bad deal. And if you're the median Fivetran user, BigQuery is going to be about twice as expensive. However, it's still not going to be that expensive. Either way, the total cost of these data warehouses and usually ends up not being that high. And then there's one more caveat with BigQuery, which is that if you have over $40,000 in spend per month, if you reach that sort of promised land, as it were, then they will switch you to slot-based pricing, which is more like Snowflake Redshift pricing. And I don't know how they line up. We didn't compare that because that wasn't really the user group we were targeting with this benchmark. So there's a bunch of caveats there, but the short version is when you compare costs, it all depends on how spiky your workload is. If it's more steady, you're better off with the pay-for-warehouse model. If it's more spiky, you're better off with the pay-per-query model. Last thing, I mentioned this at the beginning. How does this compare with those other benchmarks that I thought were unsatisfactory that drove us to do this in the first place? There are 3 that are similar. The first one is Amazon's own benchmark, Redshift versus BigQuery. It was also, they did one based on TPCH and one based on TPCDS. TPCH is basically like earlier TPCDS Junior, same idea, but not really as good. Unsurprisingly, Amazon's own benchmark showed that their data warehouse is way better. The main criticisms I have of this, that I outlined in the blog post that I wrote about this, are that Redshift, they didn't tell us how many, they didn't tell us they did partition keys or sort keys, which, as I said, if you use them over aggressively, they turn into a cheat. They use a really big Redshift cluster. And I'm guessing they didn't call up Google and ask them to lift the compute cap that you get by default when you set up BigQuery. So there was probably a little bit of a narrow type on BigQuery there. And there are a bunch of other small things that we just don't know. That's the thing. They didn't publish the source code. There's all these things they could have done that we don't know about. So, I kind of view it with skepticism that I think we all probably view what vendors own benchmarks with. The second one is there's a BI tool called Periscope. It's kind of a SQL-centric BI tool that did a Redshift versus Snowflake versus BigQuery benchmark. They only show Snowflake and Redshift in this chart because of the difficulty of making those cost comparisons with the different pricing model. They showed that Redshift was about twice as fast. It was done earlier than our benchmark, so it's quite possible Snowflake got better during that time. The other difference is that their queries are much simpler. They're just joining like a fact table or one-dimension table and doing an aggregation. So queries like that are going to be much more dominated by scan speed, which might favor Redshift, just because Redshift does have data sitting on the disks of those computers that don't have that S3 thing. So basically my criticism of this was that the queries were too simple. They don't look like real users' queries. These are too simple, and thus it's not a great comparison. They also compared to BigQuery. They did kind of a similar thing to us. It wasn't exactly the same, but they basically tried to figure out their users' actual utilization, and they got similar results. It was basically like for sort of the median user, Redshift or Snowflake was a better deal, but if you moved a little bit towards more spiky workloads, then BigQuery became a better deal. So it's very similar to our results, which is good to see. The last one is a 1.1 billion taxi rides benchmark that a guy named Mark Lipunchik published. He has included a lot of data warehouses in this benchmark. So he has it on his website. He's a consultant, and so he kind of writes these things to help run your business, I think. There are a couple issues with this from my perspective. First of all, you'll notice all the top data warehouses in this benchmark are GPU data warehouses, which you probably never heard of. And the reason is that this doesn't even have a join in it. It's just a scan with an aggregation. So that is basically just a measure of how fast you can do scans. The other thing he did is that he did the query repeatedly and then reported the fastest time. And then the last issue is that these times are really short. Like for BigQuery and Redshift, you're kind of looking at the floor here. And this is the best they can do. There are certain, just fixed costs of planning the query and such. So for those reasons, I thought it was not a great measure. The biggest one is just that it doesn't do joins. Like real queries have joins. Your scan speed is not a very important metric of the quality of your data warehouse. Interestingly, he added another warehouse to this morning, that Raffle DB, and I posted my criticism on Hacker News, and he responded. So I thought, to be fair, I should include his answer. I could have maybe put this like a little bit more nicely, but it was frank but constructive, I thought. And there was some more debate after this, but the main point he makes is that top one. He thinks, and he's not the only one, that OLAP workloads are all about scans. He thinks if you have a data warehouse, you should build a ETL pipeline that denormalizes all of your data into big, wide tables with hundreds of columns. And then all your queries will never do joins. There is a community of people who believe that. I don't believe that. I don't think that's a good approach. I think the data warehouses are so fast now, you should save yourself that work. You should just deliver the data in a normalized schema, start writing queries, and then see which ones are actually slow and work on those. I think it's premature optimization to do this all normalization approach. But there is a legitimate point of disagreement here about what is the important feature of data warehouses. So having said all that, the benchmark doesn't really differentiate them that much. Snowflake and Redshift are pretty close together. BigQuery, it's really about the pricing model. If you have either a really spiky workload or a really steady workload, then it's either going to be a great deal or a terrible deal for you. So what really matters about these data warehouses, and in my opinion, the thing that is most important is not the speed, because they're all really fast, it's the ease of use. It's how much of a pain is it to manage this data warehouse. Because often the data warehouse is kind of the stepchild of your cloud environment. Your devs are not managing it the same way they do your production database. It's really your analysts' pet, and they are not really of the kind who go and do re-indexes and things. So in my opinion, this is the most important feature that differentiates these data warehouses. And it kind of pains me to say this, especially since we're in the AWS loft. And because Redshift basically gave me a company. All of our first 50 customers were Redshift customers. It completely changed who was able to adopt data warehouses. But Redshift has fallen behind in this regard. At the end of the day, Snowflake and BigQuery are easier to manage. And so I think they do have a win there in terms of ease of use. I think there's no one who's way out ahead in terms of the performance. I think they do have an advantage right now in terms of ease of use. This wasn't true 2 years ago, but I think it is true today. Some people think it's really important that it's in the AWS Council. They just think I have to use Redshift because it's in the AWS Council. And I guess if you're one of those people, then that's how you think. But that's kind of my conclusion of all of that. So, shameless plug. If you want to get one of these things into your data warehouse, and any of these data warehouses, we can make it really, really easy. And with that, I'm happy to take questions. Yeah?
Tell me more about your ease of use. What does that mean?
Sure. It's like an accumulation of little things. So, for example, if you want to change a partition key in say Snowflake, you can just give the instruction, and then it will get rebuilt in the background. In Redshift, you have to rebuild the table. And there are command line tools that help you do that, but it's annoying. A lot of people end up not doing it because it's such a pain. There's other things like the way that views work. There's basically like an accumulation of many small things that make Redshift feel a little bit more like managing like your own database and a little less like a Portland service.
Before we take the next question, I just want to remind everyone we are giving away a Google Home very soon. I know you want to win Google Home. Hang on. Yeah, I'm going to tell you. There is a glass fishbowl, which I believe is on that table right there, but I'm not sure. Everyone put your business card in that fishbowl. If you don't have one, you can make one up on any piece of paper as long as it contains the same information, meaning your name, email, professional title, and job. So please put your information in that fishbowl. We will be giving this away in the next few minutes. Let's take the next question, please. Yes?
Yeah.
So Amazon has recently been pushing Spectrum, which is their read from S3 buckets directly with Redshift queries. That sounds like it's going down the BigQuery model. Have you thought how that's going to go into like either your benchmarking or just in general affect the Redshift performance?
Yeah, so Spectrum is interesting. Amazon is not sitting still. They're kind of doing two things that I see. This is just someone reading a blog post. They're doing Spectrum, which allows you to query data that's sitting in S3. You have to actually put the data into S3 and put it into an efficient format like Marquet, so it's complicated to operate. It does seem like it would give you some of the advantages of systems like Snowflake and BigQuery. I have done some very preliminary benchmarking of it, and if you have all of your tables in the Spectrum, and you just try to join them, the performance is not good. Having said that, they will tell you not to do this. That is not what it is intended for. The idea is if you sort of have one big table that is really huge and you don't want to load into Redshift, you can keep it in S3. So Spectrum is not really like turning Redshift into like Snowflake or BigQuery. It's solving a specific problem, which is I already have a bunch of data in S3. Now maybe that will change. But at the moment, it's not really an alternative now. It's for that one narrow use case. The other thing they're doing is Athena, which is managed Presto. So Athena is really interesting. Again, right now, you have to sort of assemble all the files in S3 and stuff and get them into the Hive Metastore, which is what Athena runs on. So it's sort of early days with Athena right now. Athena is very interesting because it separates the compute from storage. Truly, it's intended. All the tables go into S3 with Athena. And it actually has BigQuery's pricing model, except that it's based on the compressed size of the data rather than the uncompressed size, so it's about half the cost. So it's still really early. Like it's a real tinkerer's tool right now, but we'll see. We're watching it. We want to see where it goes.
Next question. Right there in the back row, sure. Right, Jack.
So is there
Yeah.
feature-wise, is there a big differences, like are any other features in one of those three? Why do you prefer one of those?
I just realized I should probably repeat the question since people are hearing. The question was, is there a big difference between the feature-wise? And there are many small differences. It's sort of hard to, there's so many things. I feel like the most important things are BigQuery, different pricing model, right? Which can be good or bad, depending on what your workload looks like. Snowflake, you can separate compute from storage. You can spin up and down warehouses at will. Those are kind of the marquee features of those two systems. The other big thing that you might not think of is BigQuery does have quotas. So if you run a lot of like update and delete operations, you will run into those quotas. But they keep getting bigger. They're almost big enough that they're no longer annoying. 6 months ago, they were really annoying. So that's the last thing I was going to call out. But that's kind of going away. So at that point, there's not that many feature differences.
Right there.
I noticed you didn't mention concurrency. I'm a consultant. We have a lot of clients that are fleeing Redshift in favor of Snowflake because of concurrency issues.
Yeah, I know what you're talking about. We have some of those too. So the question was, what about concurrency? Because I didn't talk about concurrency. It's a consultant who has a lot of customers who are moving from Redshift to Snowflake because of concurrency development. We've seen that too. So if you have a Redshift cluster and you have a lot of concurrent users, some people run into big problems where it just kind of grinds to a halt. I still am not sure whether those people just have like configuration fundamental limits? And I don't know what the answer to that is, but that is the thing that happens. And in some sense, maybe it doesn't matter. Like, if users have this problem with smart users, then like, if it was a configuration problem, the configuration was just too hard, right? So I think that is one of those pieces of these things that I've seen that. I've seen Redshift clusters go sideways over concurrency problems, and I've not seen that with the other warehouses in the last year.
Just to add on, what we've seen is sometimes with the concurrency, if the connections are not maxed out, that extra availability is not spread out. So if you have 15 concurrent connections and only one is being used, you can't maximize that whole bandwidth.
Yeah, you know, you probably know a lot more about this than I do. We're a data pipeline, and we deliver the data. There's only so many hours in the day. And when our customers have concurrency problems of this type, and we have seen this, there's only so much we can do to help them, because it's just like not our business. We sometimes refer them to consultants. So we have a few of them who we can work with, who are like, you know, that phone, like, you need to pay this guy a bunch of money, and he's going to help you keep your Redshift cluster alive. But we, at the end of the day, we're not experts in the inner workings of any of these data warehouses.
We're going to take one or two more questions, but I just want to remind everybody, if you don't have a business card and want to enter the raffle for the Google Home, you can write one up, but it has to have the full information of a business card. If you put in anything less than that, you will not win even if we pick your name.
Wait, what do you need in there?
Everything that goes on a business card, name, email, telephone, whatever.
Logo.
So you don't have to do the telephone, name, email, company name.
I just put my name in there.
Well, that entry won't be picked, so you can make another one, drop it in.
Oh, then I
Just make another one, drop it in. Don't worry. If we pick the one with just the name, we're not going to
I'll
count
figure
it.
it out and put a new one in. That's okay.
No, you can't go in the ball. That's a shame. But okay, just throw another one in there and don't worry about it. Yes.
So I have two questions. So did you compare it to the Hive itself, especially with this Hortonworks test, Hive on test? This is first one.
The question was, did we compare Hive? No. When we did those 3 data warehouses, Hive has a reputation for being slow, but first has
Right,
been a lot
that's-
faster.
But that's perception, and
Sure.
if you are going into the really big data queries, then this is where
So,
this is what Hive was.
yeah, we did compare Hive. I did actually do some work on Presto. If you go look at the GitHub repository, you'll see Presto is in there. We didn't report Presto because even after a lot of work, we thought we still didn't have it configured correctly. Any Hadoop-based system requires tons of configuration to get good performance. And we didn't believe our own numbers. We thought we still haven't got Presto set up right, and it's reporting slower than it is. And in fact, that was true. We later figured out that by changing the things, we could make it a lot faster. It's probably still not as fast as it can go. But Presto, the best performance we've gotten out of Presto is about 5 times slower than Redshift Snowflake. And Hive, in every case I've ever seen, Hive is slower than Presto. So, but then again, like I said,
Well,
maybe we still have.
That's about the data set. I mean, if the data set is really big, then MapReduce should beat it, you know, just by theoretical. And the second question, which probably you said no to the first one, and probably no for the second one as well. Did you consider the other, you know, query engines in Hadoop workspace like Apache Trill or Impala or Spark SQL? I mean, this is where a lot of people, a lot of organizations actually going.
We didn't do anything else in the Hadoop ecosystem. Like I said, we chose the ones that we see as being the most popular amongst, customers that we see, which are those 3. But there are lots of data warehouses in there. So.
Okay, last question before we do a raffle. Yes.
So I just wanted to hear your thoughts on GPU, whether you are aware of this. Specifically, like they use an architecture very similar to Snowflake, but the data is out.
Yeah. So the question is, what about GPU data warehouses, like those ones on Mark Levinchik's blog that win all the top spots? Not an expert on GPU data warehouses. Every GPU data warehouse benchmark I have ever seen has no joins. It's just a scan and an aggregation. I would really love to see someone on TPCDS on a GPU data warehouse, because I want to know I am suspicious that they do not work for joins because it doesn't make sense to me that you have to pay the cost of moving to GPU memory. But I could be wrong. I'm not an expert, so I'd really love to see something around that benchmark.
Okay, George will be. George will be here for one-on-one questions after our raffle. Please feel free to come up here and ask. Please don't steal the prize. You might win.
I know.
But anyway, feel free to come up, speak with George right after the raffle. Thank you all for coming. Thank you, George Fraser. Now let's move this thing away. Okay, let's see. Can I ask you to mix it all up? Mix it all up. Now, better than that. Can I ask you to look that way, reach in, and pull a card out? You're really not looking, you're missing the whole board. All right, you read it out.
Sure. Zafar Ali.
Zafar Ali. All right, congratulations, Zafar. Thank you all for coming.